Welcome to Examrace. This is the classical mechanics and we are here for the special theory of relativity, and that is what relativistic kinematics, the sub part of the special theory of relativity. So here we will see the relativistic transformation of velocity. We already know there is a transformation of coordinates from one to another. For example, as you know the Lorentz, that was x dash is equals to gamma times x minus vt. Okay, but if we want to convert from x to x dash, then it is gamma times x dash minus v, it's plus v t dash. Okay, these are the two coordinate from x dash to x, or from s to s dash frame, or s dash to s frame. Similarly, y dash is equals to y, and if it happens, then y is equals to y dash, and same for z dash to be z, and z is equals to z dash. Now see, for t dash it is gamma times t minus vx over c square, and here it's t equals to gamma times t dash plus v x dash over c squares. These are the transformations that we have already learned, and these are the Lorentz transformation. Now we will see how these transformation can be used to find the relativistic transformation of velocities from one frame to another frame. These are the two different conditions that we have given. Means this is what given, and these all are the condition I want to find. Means this is what I want to know from the given condition. This is a required condition. I want to require these all. For example, I want to know u dash x, u dash y, and alpha, as we have given v2 cos theta, v2 sin theta, and v2, and theta is also there. In the given condition, you can see the observer in the s frame, and this observer in s frame and the s dash frame is moving, and this s dash frame is moving with the velocity v1. Now the particle is b, and b is moving randomly with a b2 velocity b2. But when we see and when we resolve the velocity component into the horizontal and vertical, we see that v2 cos theta is the horizontal component and v1 cos theta or v2 sin theta is the vertical component. In the same way, when the observer is transformed from s to s dash frame, means now observer in s dash frame, and we have all the given conditions that is already there, and by using those conditions, means if v1 is the speed for the s dash frame, and that is moving right from left to right, but when observer is in s dash frame, it seems that s frame is receding, means s frame is moving from right to left. Okay, now we want to find the speed of that particle in the condition when observer is in s dash frame, which means if the particle is moving in u dash, then we have to find u dash, also alpha, and u dash x and u dash y. Now we start with the given conditions, means what the Lorentz equation says. So Lorentz transformation equation says that x, now we move from x frame, we want to know x frame. X frame is what? Gamma times x dash plus v1. Okay, this is the velocity for the frame, and the frame s is moving with the v1 into delta t dash. This is what we have. If it is the equation, now sorry, this is t dash. Okay, now see one thing, we will see the slight change. Means a slight change means a position is changing in x, in x dash and time. So if it is delta x, then it is also delta x dash, and this is going to be delta t dash. Similarly, if I see this delta y is equals to delta y dash, and delta z is equal to delta z dash. Now, as we know, what is time? Time is gamma times t dash plus v times x over c square. Now this is going to be the delta, and here also and here also. This is x dash v. Now you can see the two different things which are in this way, that the delta t is given, delta x is given, and if delta t and delta x is given, let them the equations. So this is the equation 1, let this be the equation 1, let this be the equation 2. So if you divide equation 1 by 2, okay, so it will become on left side delta x by delta t, on right side something else. Okay, we will see what will be the changes there.